Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder why sometimes things that should be different get measured as the same, or why measurement errors aren't always about things being scattered? All over the place, this new paper dives into a less talked about type of measurement error. And it helps us understand a lot of situations where information gets lost or squeezed together. So imagine you are trying to measure something, like someone's age. Classical measurement errors are like when your scale is a little off each time you weigh yourself, sometimes a bit too high, sometimes a bit too low, but generally around your true weight. This is like scatter, but what if instead of measuring someone's exact age, say 22 or 54, you just put them in a category like under 18 or 18 and over? Suddenly, those two different ages, 22 and 54, are treated as exactly the same. This is the opposite of scatter. This is compression, or as the researchers call it, discretization error. The paper's main idea is to introduce and model these discretization errors. They're the inverse of classical errors, which are those random blips we often worry about. While classical errors spread out measurements, making them different when they should be the same, discretization errors squish them together, making them the same when they should be different. Think about how we often categorize things in research or even in everyday life. We take something that is really continuous, like a person's exact knowledge or their precise mood, and we boil it down into a few boxes, like agree, disagree, or pass-fail. This process, where a range of true values gets collapsed into a single measurement or category, is where discretization error happens. The researchers wanted to create a way to mathematically understand these errors and, importantly, find a way to correct for them. They say that classical errors add randomness, making things different. Discretization errors take away randomness, making things the same. Classical test theory, which is the standard way many psychologists think about measurement error, assumes these random errors. The formula xt plus c, where x is the measurement, t is the true score, and c is the classical error. The key idea here is that the expected measurement for a given true score itself, that is extx, x. This means the error doesn't systematically bias the measurement up or down, but for discretization errors, it is different. If we score a measurement x and it comes from collapsed true scores t, the core idea is that the expected true score for a given measured score should be that measured score. That is etxx. This is like saying if you score someone as above 18, the expected true age for that group should be some average value representing that group. They call the error here d, and it is written as x plus dt. This means the measurement x plus the error d equals the true score t. The minus sign in xtd, which is equivalent, is a good way to remember that this error is about removing information, not adding random variation. Just like classical errors have reliability, which is how much of the measured variance is due to true score variance, discretization errors have something similar, precision. This precision is the proportion of true score variance that is retained in the measured scores. A high precision means the discretized measure is still quite informative about the true score. A low precision means a lot of information has been lost. The paper goes on to show how this applies to linear models, like when we try to predict one variable using others. They show that if we score our variables using these conditional expectations, we can get estimates for the relationships, slopes, and correlations between the true, underlying variables even if our measurements are discretized. Scroll, they even derive a correction formula for correlations and slopes, similar to what Spearman did for classical errors, but adapted for discretization. This formula uses the precision of the variables, which is like the reliability in the classical model. This framework is super useful because it can explain many existing methods. For example, polychoric relations, which are used with Likert scales or ordinal data in things like structural equation modeling, fit perfectly into this discretization model. When you use the Likert scale, you are taking a continuous underlying attitude and collapsing it into a few ordered categories. This is exactly what discretization error is about. Item response theory, or ERT, which is used to score things like tests, also fits. When an ERT model assigns a score based on a person's answers to items, it is essentially estimating their position on an underlying continuous trait. Their actual answers are discretized responses. And the IRT model's predicted score is like estimating the true score given those discretized responses. The EEP, or expected a posteriori scores in IRT, are essentially the conditional expected values we've been talking about. The paper also includes a cool figure showing how different types of discretization affect correlations. It compares a polychoric approach, where you set cutoffs, to an IRT approach, where response probabilities are used. You can see that both reduce the correlation between the measured variables compared to the true underlying variables, but the IRT model, in this example, shows a larger drop, meaning more loss of information or lower precision when using a probabilistic model. But it doesn't stop there. The model is presented as a general framework for any situation where true scores are collapsed. They discuss how it can apply to things like logistic regression, where a continuous latent variable is dichotomized to predict an outcome. They even make a connection to missing data. When data is missing, it is like those true underlying values have been collapsed into a single missing category. They also talk about misclassification, where people are assigned to the wrong category. This is another form of discretization error, because people who should be different are being treated as the same. They even provide a real-world example using data from the European Social Survey. They took data on political interest, sex, and age, and then they deliberately introduced different types of discretization errors, misclassifying sex, splitting age into two groups, and making the political interest data have missing values. They then showed how their model could be used to correct for these errors and get estimates for the relationships that were much closer to the relationships you'd find if there were no errors. The results from their applied example were pretty striking. They showed that uncorrected discretized variables led to smaller explained variances and larger standard errors for their estimates. But when they applied their correction method, their estimates became much more accurate, closer to the estimates you'd get if the data wasn't discretized at all. They highlight how the discretization of age, in particular, led to a lot of information loss, with a very low precision score. So, what is the big takeaway from all of this? The researchers have given us a powerful, unified way to think about a whole class of measurement errors that go beyond the usual random noise. They've shown that when we collapse true scores into measured scores, whether it is through explicit categories, missing values, or even misclassification, we introduce discretization errors. These errors reduce the variance we see in our measurements compared to the true underlying variables. And this can lead to underestimating relationships and a lack of power in our studies. This model provides a roadmap not just for understanding these errors, but also for correcting them. By estimating the conditional expected values and the precision of our measures, we can adjust our analyses to better reflect the true relationships between variables. This is super important for making psychology a more reliable and precise science. As the authors emphasize, it means we can build better theories and separate psychological phenomena from the noise or compression in our measurements. They suggest that we need more research focused specifically on understanding and validating different types of measurement errors to improve the quality of our data. My take on this research is that it is a really significant step forward in how we conceptualize and handle measurement error. For years, the focus has been on random error and reliability. This paper brings discretization error to the forefront and shows how it's a much more common problem than we might intuitively think, impacting everything from questionnaire scoring to missing data analysis. The idea of precision as the counterpart to reliability is really insightful. It is a reminder that not all error is about things being scattered. Sometimes it is about information being compressed, and that has its own set of consequences. One of the strengths is how general this framework is, by framing it in terms of population parameters and conditional expectations. It can be applied to a vast range of situations without needing to make very specific assumptions about the exact shape of the underlying distributions, which is a big deal compared to some highly specialized models. The applied example where they simulated and corrected for multiple types of discretization errors simultaneously really drives home the practical value of their approach. A limitation, as they themselves acknowledge, is that accurately estimating those conditional expectations and variances can be challenging in practice, especially in complex situations, or when population data isn't readily available to calibrate the estimates. Also, their correction formulas are based on linear models, so applying them to highly nonlinear relationships might require further development. But the implications are huge for anyone working with survey data, Likert scales, or any kind of measurement that involves categories or missing data. This work provides a concrete framework for improving the accuracy of their findings. It encourages researchers to think critically about how their variables are measured and what information might be lost in that process. It could lead to more robust statistical analyses and, ultimately, to a better understanding of psychological phenomena. For future research, it would be fascinating to see this framework applied to more complex models, perhaps involving non linear relationships, or even combining discretization errors with other types of measurement issues. Developing user-friendly software tools to implement these corrections would also greatly facilitate their adoption by researchers. Imagine a world where, by default, we consider not just random error but also discretization error in our analysis. That would be a huge leap forward for psychological science. What do you think about these discretization errors? Have you encountered situations where information seems to be lost in your own research or daily life? Let us know in the comments below, and if you found this breakdown helpful, please give it a thumbs up, subscribe to Rubin's Mind Lab for more science explained, and hit that notification bell so you don't miss our next video. Thanks for watching, and we'll see you next time.